Today we are going to discuss the Hardy Weinberg Equilibrium, which was given by Geoffrey Hardy and Wilhelm Weinberg. It is the founding theorem of population genetics. And to understand Hardy Weinberg Equilibrium, we should know that the evolution is a population phenomenon. It was previously the organismic phenomena or the species phenomena as described by the Lamarck and the other evolutionary biologists. But after the Darwinism, we can proudly say that evolution is a population phenomena. That means unit of evolution is a population. And the second thing is evolution can be represented as the change in gene frequencies or the allelic frequency resulting from the action of the various natural forces such as mutation, which is the ultimate source, selection and the genetic drift. And the third thing we should know that these changes can lead to the differences among the population or the species or even to the higher clades if we talk about genus and all. So these three things we should know before understanding the Hardy-Weinberg equilibrium. Now for understanding Hardy-Weinberg equilibrium, let's talk about certain allelic combinations in the population or in the individuals. Let's say if a character is present in an individual, so according to the Mendel, each character is controlled by a pair of alleles. There will be two alleles controlling a character. That means total number of alleles for that particular character will be 2 in an individual. And if there are 1000 individuals, then total number of alleles will be just double, 2000 individuals. Now let's assume there is a population of 1000 individuals, and if we look at the allelic combinations, there can be three types of combination. One is homozygous dominant individuals, which are having both dominant alleles. It is represented by capital alphabets. For example, capital A and capital A. The second individuals will be those which are heterozygous. That means they are having one dominant allele and one recessive allele. And the third individual will be homozygous recessive individuals, which are having both recessive alleles. And let's take an example. If there is a population, it is having 360 individuals homozygous dominant, 480 individuals heterozygous dominant, and 160 individuals homozygous recessive individuals. Now in this population, which are having three types of individuals, if I want to calculate the frequency or percentage of dominant or recessive allele, how it can be calculated? Let's talk about the problem number 1, calculate the frequency or percentage of the dominant allele in this population which I have discussed, hypothetical population. So we need to understand this dominant allele is present in how many individuals, how many types of individuals. So from my data of question, there are two types of individuals which are having the dominant allele. One is homozygous dominant, which are having each individual in that set is having both capital A, dominant allele, two dominant allele in each individual. And we have heterozygous individuals which are having one copy of the dominant allele. And the total number of alleles in this population will be 2000. The population size is 1000, so the number of alleles will be 2000. So simply, we'll double the homozygous individuals and we'll take the heterozygous individuals, we'll add it and we'll divide it with the total number of alleles, and then we'll multiply it with the 100. So the frequency comes out, percentage comes out will be the percentage of dominant allele. It's simple. As in my case, it is 60%. Now, if we want to calculate the frequency, it's very simple. The percentage is in terms of 100. Whenever we say 60%, 30%, 40%, it is in terms of 100. But when we talk about frequency, so it is in terms of 1. That means if a percentage is 60%, frequency will be 0.6. It's very simple. Frequency will be 0.6. So we can derive a formula for the percentage as well as the frequency. Percentage for dominant allele will be 2 into the number of homozygous dominant plus heterozygous number of heterozygous individuals divided by total number of alleles multiplied by 100. It will be the frequency, sorry, percentage. And if we remove the 100, it will be the frequency. Okay, let's move further in the Hardy Weinberg Equillibrium. So what basically Hardy Weinberg Equilibrium is? Hardy Weinberg Equilibrium is based on certain assumptions. And these assumptions are population is large, number one. Number two, the individuals in the population are randomly weighted. And number three, they have assumed that there is no evolution. There is no change in the allelic frequency. Let's see. In such population, the sum of allelic frequency, the sum of dominant allele and the recessive allele frequencies will be 1. Mathematically, I can say P plus Q is equal to 1, where P is the frequency of dominant allele and the Q is the frequency of recessive allele. So according to Hardy Weinberg, if a large random mating non-evolving population is there, the sum of frequency will be 1. P plus Q is equal to 1. Not only this, they have explained the frequencies of individuals also. And for finding out these, they have simply taken the square of their equilibrium, their equation. P plus Q is equal to 1. We will square it. P plus Q square is equal to 1 square. It will comes out as 1. So P plus Q whole square can be expanded as P square plus 2PQ plus Q square, and it is equal to 1. It is simple binomial equation. In this equation, the P square represents the frequency of homozygous dominant individuals, capital E, capital A. And 2PQ represents the frequency of heterozygous individuals, that is capital A, small a. And the Q square represents the frequency of recessive individuals, which are small a, small a. So in all, this Hardy Weinberg Equilibrium explains the sum of allelic frequencies as well as the sum of individuals in a population. And let me tell you, it is a tool. This tool tells us about the population in the current scenario is evolving in a negative direction or in a positive direction. If the sum of allelic frequency is less than 1, that indicates it's a negative evolution. Either that character or the particular allele is getting eliminated from the population, or it is going to extinct in the near future or in the future. And if the frequency sum is more than 1, that means population is evolving. Now coming to some problems which has been asked, certain questions which have been asked in the NEET examination. There are some basic questions which have been asked previously. Problem I am going to discuss is, if the frequency of dominant allele is 0.6, then calculate the number of heterozygous dominant in the population of 1000 individuals. Now we have the data. P is 0.6 and we have to calculate the number of heterozygous dominant, that means the capital A and small a individuals. So simply from this question we can find out the value of Q also. If P is 0.6, Q will be 0.4. And from this we can find out the frequency of heterozygous dominant, which is 2PQ. 2 multiplied by 0.6 multiplied by 0.4, it will comes out as 0.48. Now what is 2PQ? We have discussed 2PQ is the frequency of heterozygous dominant, and they are asking the number of heterozygous dominant. So we have got the frequency of heterozygous dominant, which is 0.48. We can say 48% of the individuals in the population of 1000 are heterozygous dominant. So the answer is very simple, it is 480. 48% of 1000, 480. Now coming to the next question, next problem. If the frequency of recessive allele is 0.3, then calculate the number of dominants in the population of 2000. The population size can be 1,000, 500 or 2,000. It has to be looked in the question very carefully. But in my question, it is 2,000. So from this question, I have Q is equal to 0.3. Now I have to calculate the individuals of dominant type. We have Q, we can easily find out the P. It will be 1 minus 0.3 will be 0.7. And if we look at the individuals, there are two types of dominant individuals. One is homozygous dominant individual, other is heterozygous dominant individual. And their frequencies are represented by P square for dominant homozygous and 2pq for dominant heterozygous. So we'll add both P square plus 2pq. We'll get the frequency of dominant individuals. Simply by putting the values of P and Q, we can find out it will be 0.91. That means 91% population is dominant. 91% out of 2000. So it will come out as 1820 individuals out of 2000 are dominated. So these are some problems of the Hardy Weinberg Equillibrium which has been asked in the previous year NEET examination, AIPNT examination, and even in the AIMS and JIPMA. Thank you.